So we're talking about vectors. We need these for physics. And towards the end of the lecture today, we're talking about vector multiplication. This is where we multiply two vectors together. Okay, and there's two standard products. They're very different that we need here. One's the dot product or the scalar product. It's where you multiply two vectors and you get a scalar. And this is the way it's defined. Okay, and the other one is the cross or vector product, which now you get a vector, okay? Its magnitude is given by the product of the magnitudes and not the cosine now, it's the sine of the angle. This turns out to what's convenient here. And you'll see this naturally arises in physics. Both, the cosine in the previous product and the sine here, they naturally arise in different situations. We'll see that in this class. Now, we need to assign a direction to this. So it's defined to be, by convention, it's perpendicular to the plane of the two vectors. And so that narrows it down to either this way or that way, right? So A cross B here, it's either going to be that way or this way. And then we use the right-hand rule. You put the two vectors together, the A and B vectors together, put your palm there, and it's how you have to push the first vector into the second vector. Your thumb will then give you the direction. It'll pick out this direction as opposed to this direction. So this is what everybody does, okay? Well, nearly everybody, I guess. All right. So just some properties here of the cross product. You'll see that when two vectors you might worry about this. You might say, well, wait a minute. It's perpendicular to the plane, but what if the vectors are collinear? Then there's an infinite number of planes. Well, you don't have to worry about that case, and why is that? When A and B are collinear, theta is equal to 0. What's the sign of 0? So it's 0. So it doesn't matter what it doesn't matter that you have a direction problem because it's 0. So it all takes care of itself. Furthermore, you'll see, when I do this cross product here, I get a certain vector. It has a direction perpendicular to the plane given by the right-hand rule, and it has a magnitude, right? What happens when I go here? What happens to the direction stays the same. Yeah, and what, I couldn't hear.
The magnitude's going to go up, right?
Yeah. In fact, it's a maximum when the vectors are perpendicular. Can you see a physical application for that? Suppose you're like tightening a bolt, right? I got a wrench and I'm tightening a bolt. Are you going to push this way or this way? Now you want to be perpendicular, right? That's where it comes up. That's one of the places where the cross product comes up. Torque, as we will see in this class, is defined by a cross product. Okay, so it's a maximum here. Let's go here. Well, it's still pointing in this direction. It's going to go, its magnitude will be less, right? What happens here? 0. Right. Now, what happens here? Yeah. And you got to remember, you got to look at the acute, the smaller of the two angles. So, R cross B here, red cross blue, I now have to go like this for the right hand. So it's going to change direction when you go here. And then here it'll be, we're back to the maximum magnitude, but in the opposite direction. Okay. Now this is kind of interesting. Let's go back to here. So A cross B, right? A cross B. What if we do B cross A? Well, the magnitude is going to be the same. Direction changes. So, mathematicians have a name for this, and it arises not just in this situation, but in other situations. It's not strictly commutative, because if you switch the order, you get the same magnitude, but the direction changes sign. So, we got to put a minus sign here. So this is called anti-commutative. Finally, you can show that it obeys the distributive law, that if you have A cross the sum of vectors, you can distribute the cross product over the sum, similar to what we've seen before in other products. Unit vectors, I cross I, has got to be 0, right? Collinear. Any vector crossed with itself has to be 0, because it's collinear. And then you'll see here that we have this cyclic permutation, we call it, in these 3 cases here. When we go in order of I, j, k, I cross j is equal to k, right? And then if I cyclically permute this is a fancy physics term, and it means cyclically, it means what it says. I move I can do this, I can do it this way. I can move the j, I can move everyone to the left by 1. So I move the j over here, I move the k over here, and the I has to come back over here. So that cyclic permutation gives me this, and it should be correct, and it is. You can verify j cross k is equal to I. Do you see it? Okay, and similarly we can do another permutation. We get k cross I is equal to j. Now a word of warning here. All of this is, well, not all of it, but nearly all of this is only true in what we call a right-handed coordinate system. Everyone uses, by convention, a right-handed coordinate system. What do they mean by that? Well, it means this. It means that I cross j is equal to k, not minus k. If I switch the I and the j here, what am I going to get when I take I cross j? Do you see it? It's going to be minus k. So that's a left-handed coordinate system. So we use a right-handed coordinate system. And it's convenient. One of the ways it's convenient is we get these nice relationships here. Otherwise, we'd have minus signs in front of here. We'd have to deal with minus signs. So by convention, as far as I know, people always deal with a right-handed coordinate system. Okay, well, you remember we found an analytical relationship for the dot product. The dot product is defined to be the product of the magnitudes times the cosine of the angle between the vectors. And we found that we can write it like this. So this is very useful. All right? We'll use this. This is the analytical. This follows from the definition of the dot product. It's kind of an analytical dot product. You don't have to worry about the geometry. You just crank through the numbers here, right? The components. Well, there's going to be one for the cross product too. It's a little bit more complicated though. So let's look at that. So here we go. Similarly to the dot product, we write down A, we cross it with B, and now we use the distributive law, right? What's this cross this? How many terms are we going to get here? There's actually 9 terms. You can, no, 1, 2, 3, 4, 5, 6, 7, 8, 9, okay? But what's this cross product? 0. 0, 0. So we're down to 6 terms, right? And here they are, and I've grouped them according to their direction. All right, now, we need to deal with it. We're going to be dealing with this. And, you know, you can memorize it, but what most people do is they think of this, that you can write this as a determinant. How many of you guys remember determinants? Okay. Well, if you don't remember, then you may not want to use this, okay? You can just look at this. You may have to look it up. You actually don't have to look it up. If you think about cyclic these are cyclically permutated terms here. If you look at this, you know, you'll notice in the I direction, we just have y and z down here. And you can see it's, you know, it's AY, BZ, and then it's the flip. It's AZ, BY. There's order to this. There's order hidden here. But it's easy to make a mistake if you try to memorize this. You know, you could be off by a sign, for example. So here's what some people do, okay? People who know determinants. This is identical to this. Now, some of you may know what this means. I'm going to, when I edit the notes, what I'm going to do is add that over on that board. Gene, pick that up. With that camera? Maybe? Okay. So, the determinant of a 3x3 matrix, one way of generating it, there are different ways. The standard way is you take the first term and then you multiply by the subdeterminant here. The 2x2 determinant is easy. The determinant of this is you do the cross multiplication, A times D minus B times C. Okay, so the determinant of this 3x3 is this times this subdeterminant. Then you have to alternate sign. It's a minus sign here, and then you got to do this subdeterminant. So you generate the subdeterminants by killing the columns and rows here. When I take J, I kill this, and I'm left with this subdeterminant. Finally, you take this with a plus sign times this subdeterminant, and you get that. And I'll leave it to you if you're interested, but you can show that when you use this is essentially definition right here. In here, you get exactly that. So this is how some people do it, and you can do it any way you want to. You can look it up. You can just look this up. And we won't often be dealing with the full thing. We'll be dealing with restricted cases that are simpler. We'll see an example of it shortly. Any questions about that? Yeah.
You say it would be easy to derive your top equation here, the analytical relationship. Derive it from the determinant.
Yeah, that's what I'm saying.
Right. But so how would that be presented in a problem where I can go, oh yeah, this is a 3x3 matrix, and then I can.
Oh, you have to come up with this.
Okay. Right.
Yep, that's up to you. So when you see the cross product here, so this is what most people do. When they see the cross product, they know that this is equal to that. And it's really easy to remember, right? IJK, you put the it's easy to remember this. Right, so that's what most people do, okay? But, you guys, we're different, right? And so you can do what you want. Just, try to do it right.
Try.
Okay, so here's an example. Now what we're going to do here in this example is deal with the dot and the cross product. This is a restricted example. The two vectors lie, I need to describe this to you here. This A vector is in the xy plane. That not real obvious in this diagram, so I'm going to write this in. Both of these vectors are in the xy plane. B is purely in the y direction. That's nice, it only has a y component. Bx and bz are what? 0. Those components are 0. So let's look at the dot product. Here's the definition. We'll do it two ways here. We're given the magnitudes. We're not given the angle between what we're given this angle, but what's that mean? This angle has to be 60. It's obvious. Okay. So the dot product is the product of the magnitudes times the cosine of 60 degrees. So if you punch this in, or this is actually a simple number, you get 40. So we're not worried about units here. So A dot B is 40. We can also do this from the analytical way with components. Remember, the dot product is going to be AX BX plus AY BY plus AZ BZ, but they have no Z components. So to do that, we have to find the components. We're not told the components, but we can easily find them. B is already, it's just a Y component. It's trivial. A has X and Y components. And you can see from the diagram that the X component is going to be the magnitude 10 times the cosine of 30 degrees. That's going to be this component right here. Okay, maybe I should have drawn dashed lines here to make this look more three-dimensional. I'll think about that. So the X component here turns out to be 8.66. It's this right here. Similarly, the Y component, I want to multiply by the sine of 30 degrees, so I get this. So B is in component form. It's purely in the Y direction. So now we use our analytical formula. I've killed the AZ/BZ term because they're 0. This is just in the plane here, XY plane. So this is supposed to be the dot product. It's supposed to be identical. It should be identical to the definition here. And you see when we plug things in, this is 0. There is no BX component. We get the same answer. So that's a check. This is a check mark. Okay, what about any questions? That's the dot product. Now the cross product of the two vectors, we're going to do A cross B. So I'm using just the long formula, right? Analytical formula that we generated. And I look along here, all the z components are 0. So that kills the first two terms. And you know that's got to be true, because where does this vector have to point? Where does the cross product have to point? It's got to be in the z direction, plus or minus z direction. Right, it's actually going to be plus, it's going to be in a positive z direction. Because these vectors are in the xy plane. Can everybody see that? So they're in the situation is kind of like this. Okay, this is A and this is B. Okay, this is the xy plane. So this collapses down to just the k term here. And if we substitute in the components, this is going to be 0. B has no x component. We get, look at that. We get, oh, we don't know. Yes, we do. Excuse me. I'm out of it. So this is 69k, and it's exactly what we got before, so I put a check mark here. So we confirmed it by a different method. Right? Yeah?
Where are the IJK coming from?
So this is in this formula right here. So remember, this is a vector. If we don't have vectors over here, it's wrong. It doesn't make any sense. So they come when you generate this formula, this analytical formula. They're naturally in there. From the determinant point of view, they're right there, and they come right there. They're right in there. And it's also in the, if you don't use determinants, it's there too. So if you look back here.
So it comes from the formula?
See, remember when we discussed how this would be done? You do this cross this. They're along for the ride. They're in there, and they have to be. They're in there because they have to be. Now, we can do it. This is essentially the same, but instead of using this, which I gather most of you are going to be doing, if those of you want to do it this way, we can do it this way. This is kind of compact. We just fill in the matrix here. This means determinant, okay? But this is a matrix. So this means the bars here mean the determinant of this matrix. We just fill in the values here. We got the IJK, and here's AX, AY, AZ, and there's only a BY. And then we go through here, we take this times this subdeterminant, that's going to be 0. Minus this times this subdeterminant, which is also going to be 0, as it should be. It's only going to be in the k direction. Finally, here we get this times this subdeterminant, which is that times that minus that times that. Well, that's 0, so it ends up being the same answer. Same answer. From a slightly different point of view than this, from the determinant point of view. Yes?
With respect to the answer, so what does that mean to me? 69 with the k hat.
So the resultant vector, this cross product here, C, we've been calling it before, has a magnitude of 69 and it's pointing in the positive k direction. That's what it means.
And you said we don't care about units.
Yeah, this is just math right now. There's no reason for us we don't have to worry about it. But it's later, you know, torque. This could be a torque. We're going to see that this is naturally torque. Maximum at 90 degrees, as you all know, as everyone knows, as kids know. You know, if you're going to tighten something, you want the force to be perpendicular to this radius vector here. This will be in units of torque, which is newtons times meters. Yes?
So if it's just 69k, it's just going straight on along the z-axis at magnitude of 69?
That's right.
All right.
That's right. Any more questions? Okay. So, you know, I can understand there's a little confusion here, but, you know, so nearly everybody, the way they understand this is by using it, and we're going to be using this. Okay, any other questions? Oh, I think that's it for this. Yeah. Let's see, I need to... Okay, so at this point, the next appropriate thing to do is to go back and look at kinematics, but now not just in one dimension, looking at it in higher dimensions, 2 and 3 dimensions. So we're going to redo, essentially generalize that chapter that we did on kinematics in 1 dimension. And I'm getting rid of the word rectilinear. I don't think it's appropriate at this level. I mentioned that in an email message. So, imagine we have some body, technically a particle. We don't want to worry about any spatial, a body could be big like this. So, technically, we're going to deal with a particle, right? That's what we've been dealing with. That's what we dealt with in the one-dimensional kinematics chapter. So here's a particle at some time. This is a math type problem. I can fix this. Okay, this should have an R over it right there. Let's say at a particular time the particle's at this location. How do we describe? We need, and in general it's going to be moving, right? Could be subjected to forces, could be moving around. We need to be able to describe that. So we do it. Before we did it with just an x of t. Now we have to generalize, and we generalize to a vector, r of t. And it has an x component, and it's going to be uniquely specified by some x component, y component, and z component. And these can be changing in time. Here's what it is in just an instant here. So at this instant, you can see that the x component is 3. Now this is, you have to imagine this in 3 dimensions, right? This is a perspective drawing. So that's why it's sometimes useful to use this, okay? So the Tinker Toys, yeah, useful. So x, y, and z, we move along here 3 meters. And then to that, you can see that we need, in the y direction, we need to go 4 meters along here. Okay, and then we got to go up 5 meters when we get to our point. So we would describe this point at this moment of time by this vector, this 3 position vector. And so what we're going to be doing now is just like a triplication, I guess. Because from x of t, what we did for the one-dimensional case, we're just going to triplicate that in 3 directions. Whatever word, whatever you want to use, So we got to deal with velocity and acceleration here, and it's natural to define them with starting off with the displacement. Here's the change in position, the final minus the initial. So you can see here that I have a particle and it's moving in this direction. This is its in this space here, x, y, z space. We call this path the trajectory of the particle, as many of you know. Okay, so it's moving like this, some general path. The displacement over some time interval, delta t. If this is the final, this is the initial. The displacement is the difference. Oh, remember we talked about vector differences, right? The 2 vectors here are naturally, the tails are connected. So the displacement has to point in this direction, because when I add r of t1 to this, I've got to get r2. So the arrow has to go, not only does it go between the 2 points here, but it's got to go in that direction. That's the displacement, the final minus the initial. Okay, now what do we do? What's next? Remember? We shrink the time interval down. We take the limit as delta t goes to 0. What's going to happen? So you can see here, I've drawn different displacements here for different times. So here's t1, we're fixing t1, the particle's here. Here's a much later time, relatively much later time, there's the displacement. As I start to shrink the delta t, the displacement goes there, and then in the limit as I go to 0, where is it going to point? Well, we have a word for this. I've got a curve. Whenever any curve, smooth curve, and I pick a point, that's a particular I want to be general here. What is this line right here? Yeah, we call it the tangent. It's, I don't know how to describe it. It has the same slope as the curve at this point. That's the tangent to the curve. So, the limit as delta t goes to 0 of delta r over delta t. We're going to define that to be the velocity, just like we did in one dimension. We're just extending it to 3 dimensions. So the velocity is tangent to the position, to the trajectory. The velocity is always tangent. So this is pretty obvious to most people, but I know that I know students can have some trouble with this. In fact, this will come up in the future, and I'll try to trick you into. Okay, I'll do it right now. Maybe it's not going to come up. Suppose I have uniform circular motion. We're going to talk about that next. I think, yeah. Uniform circular motion is motion in a circle with constant speed. But the velocity is continually changing, right? So you can see here, this particle is moving around at a constant speed, but its velocity is continually changing. The magnitude of the vector is constant. So suppose I have a string, and we'll do this demonstration tomorrow or the next day. It's called a conical pendulum. Okay, we'll have a string and a mass, and I'll bring the apparatus in. Suppose at this point, let's say right here, I cut the string, or I burn it. Another way of doing it is to burn the string. But there's a little time, so a practical way would be to actually burn the string. So suppose all of a sudden here, I cut the string somehow. I disconnect it. What's this particle going to do? What's the mass going to do on the end here? Well, now it doesn't have this. There's a force here that's keeping this in circular motion. It's gone now. So what's it going to do? It's going to go into what we call projectile motion, and we'll start talking about that today. But which direction is it going to go? In the direction of its velocity that it has just before I cut the string, which is tangent to the trajectory. Okay, so that's just what we saw here. The velocity here, if this is the direction of motion at this point in time, this is the instantaneous velocity of the particle right there. So if I remove all constraints, at this moment, it's just going to head in that direction. Okay, so we can write r as the sum here. This is just this triplication thing of the one-dimensional case. We have our one-dimensional case in the 3 different directions, 3 different Cartesian directions. This is the x velocity, this is the y velocity, this is the z velocity. Now we got to do this again because, as we'll see in dynamics, forces cause acceleration. So it's the same idea, but instead of delta r delta t, it's going to be delta v delta t. This is the average acceleration. We take the limit as delta t goes to 0, and we get the useful instantaneous acceleration, which we normally just call the acceleration. It's going from differential calculus, we write it like this, dv dt. And because if you use the sum, you can think of it as the sum of the x, y, and z components, we just get the vector sum of the individual accelerations in the x and y and z directions. Okay, so here I already started to talk about this. So uniform circular motion, that word uniform means constant speed. This is a very common case in physics. We'll deal with this a lot in this course. So let's say at time t is equal to 0, the particle's here. And then it's moving with constant speed, but the velocity is continually changing because the velocity is not just the magnitude, it's the direction. So if either or both of those change, you have a non-zero acceleration. So there is acceleration here. And that's important, and we will there's a formula for the acceleration. We'll derive that later on in the course. But for right now, we just want to notice that we have this constant speed motion here. At this point in time, the velocity is pointing in the y direction, and it's given by the speed times the unit vector in the y direction. And here's its position vector. A quarter of the t is the period here, the time to go around once. At a quarter of a cycle later, It's going to be up here. It's going to be pointing this way with the same magnitude, but now pointing in the minus x direction. And its position vector is r times j, etc., right? And then finally, I didn't, yeah, I put it on here. I went around here, and the final point, it's come back to here. So now we had better be right where we were before, but we've gone through one period. So this should be the same. Yeah, they're the same. Very simple example. But you want to make sure you understand stuff like this, right? That's why it's here. Anybody have any questions? All right. So, remember what we did in one dimension? Once we talked about the general motion in one dimension, we specialized to the case of constant acceleration. That's an important case in physics, as we will see. And what we're going to find is, you know, if you have a constant force, you have a constant acceleration. That's where we're headed in the dynamics. We'll eventually get there. But that's why often there are constant forces. So that means acceleration has to be constant. So what we're doing differently now is we're outside of one dimension. And so let's look in preparation for the standard application here, which is projectile motion. We're going to look at constant acceleration in 2 dimensions. So all this means is, here's what we had before. Remember, this was one of our 3 equations that we used to solve problems, right? Here's the other one, and here's the no-time equation. So we can solve any kind of problem of constant acceleration in one dimension with those equations. Now we just have a duplication here in the y direction. We don't call this a now. We call it the acceleration in the x direction, which is assumed to be constant. And now we have some other arbitrarily constant acceleration in the y direction. So we just write down the same equation, but wherever we see an x, we replace it with a y. So here's the velocity relationship for constant acceleration in the x and y direction. We can unify these two with vector language, right? This is the x component of the velocity. This is the y component. And we know that the full vector velocity is just going to be the x component in the y direction plus the y component in the z direction. So when I do that, I can write this like this. I can combine these two, unify them, and get this. Here's our position versus time relationship. We have, again, a duplication here. And we can do the same trick. You can multiply this equation by I, multiply this by j, and add them together, and you get this. Now, often when we do problems, we don't deal with the vectors here. We just deal with the component equations, because we're getting to the point here. We're plugging numbers in. This can be clumsy here because you've got to carry these vectors along. But there are cases where this is useful. And I can think of one of them is the famous monkey hunter demonstration. Who remembers the monkey hunter demonstration? Oh, wow.
Sounds awesome.
Yeah, you guys will like it. Usually our students here like it. And it takes up the whole area here. So that's coming. In fact, it's coming pretty quickly. It might be, I don't want to think about it. It takes time to set up. Okay, so we will use this. But usually this is just for sort of theoretical purposes. It's nice and tidily, you know, we can compactly represent things. When we actually get down to the calculations, usually we're dealing with the component equations. And so the no-time equation here, now this is a little different. This is a scalar. We just simply add, there's no unit vectors here. You just want to add the left and the right-hand sides, and then use Pythagoras here, and you get this. Oh, I take it I lied. You have to recognize that, yeah, you need to recognize that when you add these two things together, you've actually got a dot product there. Do you see the dot product? Forget the 2. You see this is x component, product, plus, it's like a dot product. So you need to recognize that you can write that like that. So there are some vectors in here. Okay, so this is just a prelude to standard application of constant acceleration in 2 dimensions. And in this case, for projectile motion, we're going to call x the horizontal coordinate, y the vertical component. We're going to choose y to be positive upward. Now, in the 2000, 3000, 4000 level mechanics, it's often convenient here to choose y to be positive downward. And I've discovered the hard way that it's not good for students at this level. Okay, we're going to, everything we do here, when we're in a gravitational, when we're in gravity like this, we're going to call y positive upward. It's better to do it, trust me, it's better to do it that way, okay? So in this case, we have to write the acceleration then, and we talked about this before in free fall in 1 dimension. It's going to be minus g times j. It's in the negative direction. G is, by definition, a positive quantity. It's the magnitude of the acceleration due to gravity. And what's the acceleration in the x direction? 0. Okay, so what does that mean? What's the x motion going to look like? If there's no acceleration in the x direction, it's just going to be constant x velocity. And this is obvious, I think, but if you feel funny about it, you can go back here and look at this equation. When ax is equal to 0, the velocity is constant. The x velocity is constant. The y velocity, on the other hand, is going to behave like we saw in free fall in 1 dimension. We've got this minus, we substitute minus g for ay here, and we get this. So here are the 3, we've seen these before, except everywhere there's an y, we had an x before. So this is just 1-dimensional constant acceleration. And you'll notice something here. I need to point this out to you. Physicists have a name for a situation like this. The x motion and the y motions are uncoupled. They don't influence each other at all. We have only x quantities up here and only y quantities down here. So projectile motion is really the superposition. We add together constant velocity motion in the x direction and free fall in the y direction. Now this has a consequence. I don't expect you to understand that right now, but that's what we're going to talk about it now, okay? As you could probably imagine, we're going to do a lot of projectile motion problems. The simplest, non-trivial case is where the particle is projected horizontally. So at time t is equal to 0, ignore this for the moment. At time t is equal to 0, we somehow, with a spring gun or gunpowder or whatever you want to imagine, this object here is given an initial velocity that's purely horizontal in the x direction. This is the simplest case. We'll generalize this later, not today, but in the future we will, okay? So what's the trajectory going to look like? Well, you know, it's going to go like that, right? It's going to be curved, it's going to go like this due to the acceleration due to gravity. Now, suppose we looked at this object at equal time intervals. So do you know how you can do that? Actually really do it? It's like old technology. What you do is you darken the room and you have a strobe light flashing at equal time intervals, and you open the shutter of a camera. So what you're going to see here is, and let's say we at time t is equal to 0, it's open. We see the object here. Okay. The shutter is open. The light flashes. The strobe light flashes when it's here, and then some delta t later, it's going to flash and it's going to be here. And then here's the next time it's going to be here. And you'll notice that in the x direction, what do you see here? How do you describe the motion in the x direction?
Constant.
It's constant velocity. Over equal time intervals, it's covering the same distance. Its velocity in the x direction is constant, which has to be the case because there's no acceleration. So, another way of looking at this, literally looking at this, is suppose you looked from above in this motion here. You look above, and you don't have any depth, you can't see any depth here. You have no depth perception or whatever. This is projected out. You can't see this. Okay, so you have to be actually sufficiently far away or use a lens or something. Because otherwise you could pick up on the motion this way. But we're imagining we don't see that here. We're projecting out the y motion. That's what people say. What am I going to see? I see constant velocity in one dimension. In the x direction, I see constant velocity. What do I see if I look this way? And I project out the x motion? What do I see?
Y.
We have a name for this. Yeah, so I just see the y motion, and what's it doing? It's free fall, released from rest. So, there's an interesting consequence here. Suppose at the same time that this is projected here, an object is released from rest over here. So I have two bodies here. They're released simultaneously. One of them's is projected this way, and they're at the same height. They're at the same vertical location here. And what would happen if you take a strobe photograph of this? And our textbook should have a strobe photograph of this. I can't remember if it does or not. What's going to happen at equal time intervals? Well, we know that this is going to speed up, right? This is free fall. It's going to be covering more and more distance at equal time intervals. But because the y, what difference do I see when I look this way at those two objects? They're the same because they have the same y initial value and the same, all I see is the y coordinate here, and they have the same y motion. The x motion is independent. It doesn't do anything to this motion. So at equal time, they have to be here. So which one's going to strike the bottom first?
Same time.
Same time. That's a prediction, and we can test it. Okay, so it's an ingeniously simple device. So look at this. You cock it. Okay, so remember this, okay? So if I put this horizontally, and I put these two balls on here, what's going to happen? So imagine these balls are here, right? And you're looking down this way, okay? I go like this. This thing abruptly falls out from underneath one. What's this one going to do? It's going to be this one. What's the other one going to do? It gets projected horizontally, if I hold it horizontally. So they both should strike the table at the same time. So you can watch, and you should, but the sound is going to give it away, whether it's simultaneous or not, right? So I'm going to do this on 3, 1, 2, 3. Wow, that was close, right? I heard just one collision. Did you guys? Okay. Well, we're not done with this. Okay. I'm going to incline it as much as I can this way without these things falling off. Okay, I'm going to do it this way and fire it. Now what's going to happen? First, let's do the simpler thing first. What's going to happen here? Same thing here. Right? But what about this one? What's different in this? How do we, as physicists, what do we say is different here?
As an initial downward.
Yes, that's a precise physical statement. The initial velocity now is not horizontal, it's going to be down like that. So what's going to happen? What should happen? It should hit first. So this you have to kind of, this is tough to see, okay? But I'll do it on 3. I'm going to incline this. 1, 2. Well, I heard the difference. Now, I don't know if you guys could see which one hit first, but it was the one out here. Are we done? Pardon me? Yep. Let's go the other way. That's right. That's what physicists do, right? They just try to do everything. Just play around with something, right? So I'm going to now do it this way. I'm going to incline it this way. So again, thank you. Now this is not going to be as clean because you can see, you can throw it to me, I can catch. Okay. Now there's a potential problem here, This one is good, might get kicked up a little bit, right? And could be some problems here, but let's just do it. What do we expect is going to happen here? Which one's going to hit first?
Straight shot.
So now, because we're projecting it this way, it's just the opposite of forward. This one should hit first. Yeah. So let's see if it does. You guys, I can't tell. I can just listen to the sound, but you guys can, maybe you can see it. 1, 2, 3. Did it? Okay, good. Now, if it didn't, if we projected this up here and the other one hit first, that's an interesting observation. Physicists love that kind of stuff. Now, it's certainly going to be due to some experimental artifact, something weird, but this is how discoveries are made. This is often how discoveries are made.
What about if the one being projected, like through a rifle has rifling to spiral it? Is that going to affect the...
Yeah, somebody actually mentioned something about this last week. There can be some gyroscopic effects here. So this bullet it's got angular momentum into the course. We'll get there. So please try to remember this. So rifling has come up twice now, okay? So I'm going to depend upon you guys to bring this up when we get to angular momentum. Yeah. The answer is, in this case, I don't think it'll make, well, you'd have to, without air drag, it won't make any difference in this demonstration, okay? But yeah, let's talk about rifling. I've never discussed, I've taught this course for a long time, many times, over a long period of time. And no one's ever brought up rifling, believe it or not. So that's a good application of angular momentum. But that's the last thing, almost the last thing. The last thing is gravity. Is gravitation, okay? And orbital motion. That's the last thing we do. But just before that will be angular momentum. So please bring up rifling. Okay, so any questions? This is a classic. All mechanics books should have an actual strobographic picture of this, and you can see in the picture that they strike at the same time here. And our textbook should have it, but I can't remember. So the next thing to do, and we're hardly going to touch on this, but we need to do an example. Quantitative example. So again, this is for horizontal projection, the simplest non-trivial case. We're plugging numbers in here, and this is what part of what physics is all about. Is you specify an initial height that the object's projected horizontally with a certain speed. We can predict where it's going to land. That's not all what physics is about, but that's a big part of it. The whole idea of you've got a physical system and initially it's all specified, and you want to know how it evolves in time. In this case, we want to know what the range is, how far it goes. We can calculate that. So we'll do that. We'll start off with that tomorrow. Okay. Anybody have any questions? Okay. The quiz is due Thursday at 3, right?